Welcome to BKW Physics. I'm Mr. McConnelly. Today we're going to talk about sound, and we're going to go with the Doppler shift. Just as a reminder, sound is a longitudinal wave, and longitudinal waves are made up of compressions and rarefactions. Compressions and rarefactions. The particles travel in the same direction as the actual wave is moving. Now, three words underneath sound that I wanted to highlight real quickly were the pitch, loudness, and sound level. Now, when we say pitch in music class, or wherever you've heard that before, what would be the translation for physics class? What's the word that would take its place? Frequency. Frequency. Correct. Thank you. A frequency. So the pitch of the wave is the frequency of vibration. How often it's vibrating. If it vibrates more often, is that a high note or a low note? High note. High note. If it vibrates a few times slowly, that'd be a low note. Loudness is amplitude. And it's directly related to, I heard someone say in the front, energy. Directly related to energy is amplitude, how tall the wave is from its relaxed position. But there's another one, you might not even know what I'm referring to here, but if I say the sound level, I'm basically saying there's got to be a scale to measure sound. You're like, it's loud. Okay, how loud? Well, there's actually a scale called the decibel scale. And a decibel scale just gives us a relative comparison so we can say, oh, okay, you know, this is loud and this is louder because the number's higher. And it gives you a way to compare things. That's all it really does for us. So when you see decibels, it's just a comparison type of thing. All right, moving into the real topic for today, though, is the Doppler shift. This is especially apparent in sound waves, but it does occur in all waves. And you've heard of Doppler radar. That's not the easiest one to understand right now. So we're going to start with the easiest one to understand, which would be how you hear the Doppler shift when you're at a NASCAR race.
Yeah, you hear.
Notice what the frequency is doing. Notice what the loudness is doing. Okay? They're changing. So first of all, obviously if a NASCAR is coming towards you, it's going to go from quiet to louder. It's going to get louder as it comes closer to you. Yeah, we got that. That's the loudness. That's the amplitude. But what is happening to the frequency? Because something's happening weird there. Because you hear it go. That's exaggerated a little bit, but you hear but you hear that the frequency going and dropping off. It's kind of a weird thing to be happening. And how is that possibly happening? Well, I guess I'll start, I think I'll draw it first, and then I'll show you a little demonstration device. So, if you have an object here, X marks the spot, and it's making a sound, that sound is going to travel outward three-dimensionally in all directions. So the sound just goes boom, out from that object. So if you have a loud sound, the wave fronts are going to travel outward, and I can draw it basically as concentric circles, and you're imagining that this sound wave is traveling out. So, if the frequency here was 200 hertz, then the frequency here would be 200 hertz, and here, 200. Okay, it's 200. Now the amplitude might drop off, because as the sound travels through the air, it might fade, get quieter. So the amplitude might be dropping, but the frequency would remain the same. That's not the Doppler shift. What the Doppler shift is if that object, X marks the spot, is moving. We'll say it's moving to the right for this example. If you move quick enough, it doesn't happen when you move slowly. If I walk across the room like this, you're not noticing any Doppler shift because I'm moving too slowly. But as you start to move quickly, remember, what's the speed of sound waves? Yep, the velocity is 331 meters per second, or 3.3 E2. So it's moving that quick. So if you start moving kind of, not that fast, but you're starting to move quickly, now what happens is, remember, the wave is moving out in all directions, and you're starting to keep up with the wave. on the one side. See what I've drawn here? You're actually sort of keeping up with the waves on the right-hand side of my picture, and the waves on the left-hand side of the picture, you're running away from them. So what you're doing is you're creating this effect where the waves are getting swooshed here and stretched here. Well, remember, wave fronts indicate how often the waves are hitting you. In other words, the frequency. So what's the frequency? If this one in the middle was 200 hertz, and these are closer together, what might be a possible number here? 260, okay, fine. We're totally making up the numbers. It doesn't really matter right now. What might the frequency be? I'm going to erase this picture. It's not really useful anymore. What might the frequency be on this side? 180. Fine. Making up the numbers does not really matter right now. But what you will notice, this is the NASCAR effect. Neo, neo. What happens as the car is coming towards you, the sound is squished in front of the car, because the car is moving pretty quick. So the sound is all crunched up in the front. You hear a high note. As it passes you, it goes to what you would actually expect the engine to sound like, the actual frequency of the engine, and then it actually drops lower than the engine should actually sound. So it goes high, normal, and low as it passes you. That's the Doppler effect. It is pretty cool. It's nice. And this Doppler effect happens not just in sound. It happens in a lot of things, but sound's the easiest one to start with today. Well, as you may guess, there's an equation to figure this all out, because we are in physics class. If you want to know what the frequency is over here, the part where it's all stretched out, you're going to use this. You're going to use f prime equals f naught v wave divided v wave minus v source. I know it seems really complex at first. It's really not that hard to use. I'm also going to write the equation on the right-hand side because the equation is frighteningly familiar. Really only one thing changes in the equation. Put a plus sign on the bottom. Okay. So, actually, you know what? I think I did it backwards. If the frequency is getting larger, it's coming at you. So if it's coming at you, you gotta get, this has to be the minus 1, this has to be the plus 1. Change that in your notes right now. Okay? The way I'm figuring that out is because I'm thinking of how big the number is on the bottom of the fraction versus the top of the fraction, and I know the way the numbers have to work, so I wrote it backwards in my notes. Alright, so, boom, here's the equation. What does it mean? Let's label these real quick. This is the initial, or the frequency that the thing making the sound is the frequency it's making if it weren't moving. Okay? What do you want to call it? The normal frequency? This is the frequency you hear because of the Doppler shift. So this is the changed frequency. You can call it something else if you want it. What's V wave? Well, in this case, since we're talking about, for our specific example, we're talking about a sound wave, we're talking what's the velocity of sound. Now, if you're talking about later on we talk about a light example, because you can do the Doppler shift with light, then that number would be light instead of sound. You get how that works? And remember, sound is affected by the temperature outside, so sometimes you have to go ahead and calculate some information about this to get the right answer, because if it's really hot or really cold out, it's going to change the speed of the wave. This is how fast the velocity that the sound is moving. Now, I want to be real clear about something there. The thing making the sound can move. In other words, the NASCAR can be the thing making the sound and it's moving, or you could do it another way. There could be an object over there making a sound, big loud sound, and if you move towards it, you're going to get the same effect. Either the sound could be moving, or you could be moving towards the sound. Either way, It's just basically the relative difference in speed between the sound object and the listening object. Okay? I guess the last thing I want to do, and then as a class we're going to do some examples. Last thing I want to do is, what do you use the Doppler shift for? You've heard the Doppler radar thing, and especially where we live here in Bern, they have actually a Doppler radar ball, if you will, pretty close to us. What does that do? How is that getting how is that like telling you the weather? What is it doing? Think about what this is. How could that thing be telling you the weather?
Which way the clouds are moving.
Yeah, because it's sending out a signal. Think of it just sending out a signal. Boom! That signal will hit clouds and weather, and it'll bounce back. If the waves are closer together, that tells you that the weather's coming towards you. If the waves are further apart, it tells you the weather's going away from you. That's the most simple thought process of how this works. But then based on how fast it's moving towards or away, is going to change the Doppler shift diagram, and the computer can calculate exactly what's going on. How about an ultrasound? So you like wreck your knee, or someday you're getting ultrasound for a pregnancy. How does that work? How does that work? Well, again, you're sending waves into your body, they're hitting objects, and then they bounce back and they're shifted, either together or apart. And that can help with computer imaging. It can help create a picture of what's going on inside. So for today,